Hello everybody, this is a problem set lecture to accompany the thermal physics lecture on states of matter, latent heat, and heating curves. There will be 4 problems worked. Let's get started. Problem 1 is all about heat temperature curves. Here we have an unknown material that's heated with a constant power heating source. See graph to the right. What is the melting point of the substance? What's the boiling point? And a few other questions. Let's take a look at our heating curve. On our vertical axis we have temperature, and on our horizontal axis we have time in minutes. However, it's a constant power source, which means a constant energy per unit time. So we could also relate this horizontal axis to heat that we've added. It should be a constant amount of heat per minute, so it would also be proportional to heat. But anyway, question 1, what is the melting point of the substance? The melting point is the temperature at which the object changes phase between solid and liquid. Well, we know that that occurs at a constant temperature. So it's going to be the point where we're adding heat, but our temperature is not changing. It's going to be either this point right here or this point up here. However, we know that the melting temperature is below the boiling temperature. So this plateau right here has to be melting. And that occurs at 55 degrees. What is the boiling point of the substance? Well, again, the boiling point is the temperature at which boiling occurs, and it occurs at a constant temperature, so there's going to be no change in temperature during boiling. That's going to be up here, the higher plateau. So that is going to be at about 95 degrees Celsius. During what times is the substance completely solid? Well, during the solid phase, when we add heat, the temperature is going to increase, or when we subtract heat, the temperature is going to decrease, and we know the temperature is going to be below the melting point. So it has to be here. This is our solid, so that's about 0 to 10 minutes. 0 to 10 minutes. During what times is the substance completely liquid? Well, after, if we have solid, then we melt it. It's going to be completely liquid after that as we keep adding heat, and the temperature is going to increase here. Liquid. Can't spell liquid. Liquid. So that's about 17.5 to 30 minutes. About 17.5 to 30 minutes. When is the substance a mixture of liquid and solid? Well, we're only going to have a mixture of 2 different states of phase, or 2 different states, when we're in the process of changing phase. So that's going to be during melting or boiling, or freezing or condensing. So if we're at a mixture of liquid and solid, that means we're somewhere between this solid phase down here and this liquid phase up here. So that's going to occur down here during melting, which takes place between about 10 minutes and 17.5 minutes. Now, my answers might not be completely accurate, but this is just to get you a feel for what parts of the graph represent what different states of matter. If we had more grid lines on the graph, it would be easier to read off a value. When is the substance a mixture of liquid and gas? Well, that's going to be during boiling. It's the only time we have a mixture of liquid and gas. Once we're fully boiled, it's all gas. Before boiling, it's all liquid. And so that's going to be between about 30 and 35 minutes. So at these melting points, at the boiling point, we can actually have 2 states coexisting at the same time. But those are the only temperatures in which we'll have 2 states coexisting, at least as long as our substance is well mixed. And they'll coexist at the same temperature as well. Problem 2, latent heat. 200 calories, capital C calories, which is actually kilocalories. Candy bar contains 837,000 joules of energy. How many grams of water at 100 degrees Celsius could that much energy vaporize? The latent heat of vaporization of water is 2.26 times 10 to the 6 joules per kilogram. So I'm going to start by sketching out our heat temperature curve, just sketching it out. And this is for water, and I know that water boils at 100 degrees Celsius. So we're starting right at the boiling point, so that's good. And we're going to add heat right there. And since we are boiling our water, all of our heat is going to go into vaporization. So we use the equation Q equals mL. We know the heat energy added. We know the latent heat of vaporization of water. So we just need to solve for, well, how many grams of water? That's the mass. So divide both sides by LV, latent heat of vaporization. We get mass equals Q over latent heat of vaporization, which is 837,000 joules divided by 2.26 times 10 to the 6 joules per kilogram. Let's go back one. Plug that into a calculator. 837,000 divided by 2.26 gives me 0.370. But let's be careful about the units. Joules divided by joules per kilogram is going to give us units of kilograms. And this asks how many grams. Since there are 10 to the 3 grams in a kilogram, I just need to multiply by 10 to the 3. It's going to be 370 grams of water. It's equal to M. Next question, latent heat and power. A styrofoam container used as a picnic cooler contains a block of ice at 0 degrees Celsius. If 455 grams of ice melts in 0.80 hours, how much heat energy per second is passing through the walls of the container? The heat of fusion is 3.33 times 10 to the 5 joules per kilogram. Answer in watts or kilowatts. Okay, so again I'm going to start by sketching out the heat temperature curve. Temperature up here, heat down here. All the heat temperature curves look the same. They look something like this. And this is water. And it says it's starting as ice at 0 degrees Celsius. We know that the melting point of ice is 0 degrees Celsius. So we are starting out right here. And we know that we're going to be adding heat to it. So we're going to be going to the right along that heating curve. It says 455 grams of ice melts. That's the mass. In 0.80 hours, that's the time it takes. We want how much energy per second, or power, is passing through the walls of the container. So that's P that we're looking for. We're given the heat of fusion of ice, and that's it. So if we want to find the power, that's the energy per unit time, we can start by finding the energy using our Q equals mL equation. And since we're melting our ice, that's the latent heat of fusion. So we have 455 grams of ice is our mass times 3.33 times 10 to the 5 joules per kilogram. We would multiply this out, but we have grams over here and kilograms down here. So we're going to need to convert one of them in order to cancel out the units. I'm going to convert the grams to kilograms. There are 1,000 grams in a kilogram, so I'm just going to move the decimal place over 3, and it becomes 0.455 kilograms times 3.33 times 10 to the 5 joules per kilogram. We're left with joules. That'll give us our heat. Q equals 0.455 times 3.33 times 10 to the 5. 1515 actually. Okay. 151515 joules, and we'll round that later. It wants us to find the heat per second, so that's the power, and power is energy or work over time. Since it's heat per second, I'm going to do heat over time. The heat is 151515 joules, and the time is 0.80 hours. but I need to convert that to seconds in order to get it in units of watts. So I'm just going to do 0.80 hours. There are 60 minutes in an hour and 60 seconds in a minute. So that's going to give us our answer, our time in seconds. 2880 seconds. So our power is then 151515 over 2880 joules per second, which gives us 52.6 joules per second, or 52.6 watts. Last question, and this is going to be a big one, so brace yourselves. It's not hard, it's just a multi-part question, so it's going to take a little bit of time. How much energy is required to change a 35-gram ice cube from ice at negative 14 degrees Celsius to steam at 108 degrees Celsius? The specific heat of ice is 2090 joules per kilogram degree Celsius. Specific heat of water is 4186 joules per kilogram degree Celsius. The specific heat of steam is 2010 joules per kilogram degree Celsius. The heat of fusion is 3.33 times 10 to the 5 joules per kilogram, and the heat of vaporization is 2.26 times 10 to the 6 joules per kilogram. So, first of all, let's identify variables. We're given the mass. We're given the initial state of matter, ice, and the initial temperature. We're given the final state of matter and the final temperature. So let's sketch out our heating curve for this substance. It is water, so that's nice and lucky. Temperature against heat. It's always going to be a slope and a plateau, and a slope and a plateau, and another slope. We know for water this is at 0 degrees, and also for water the boiling point is 100 degrees. So we're starting in the solid form, and it's negative 14 degrees Celsius. So this is the solid section here, and it's below the boiling point. So we're going to start here. And we end up in steam, so that's the gas form, at 108. That's above the boiling point. So that's my T final. So if we're adding heat to get from this dot to this dot, that's going to be 1, 2, 3, 4, 5 steps in order to find the total heat. So I'm going to label them 1, 2, 3, 4, 5. Now we know the equations for increasing temperature are Q equals mc delta T. So that's going to cover sections 1, 3, and 5. And we know the temperature for phase change is Q equals mL. So that's going to cover sections 2 and 4, the two phase changes. All we're going to need to do is add up all of those heats from those 5 sections, and we'll get the total heat. Okay. So we can get started, but there is one thing we want to notice. The mass we're given is in units of grams, and all of our specific heats and latent heats have units of kilograms. So I'm going to just convert my mass to kilograms. 35 grams is 0.035 kilograms. And then I'm going to just get started calculating. In section 1, we're increasing the temperature of the solid ice. So we're going to use Q equals mc delta T. M is 0.035 kilograms times C, which is the specific heat of ice. Let's see, specific heat of ice is 2090 joules per kilogram degree Celsius. And the change in temperature of the ice. Well, since it starts at negative 14 and it goes to 0, the change in temperature is positive 14. Calculate that out. 14 times 2090 times 0.035 gives me 1024 joules. Section 2. Q equals ml. Since we're going from solid to liquid, it's going to be the phase change between solid and liquid, so we're going to have to use the heat of fusion. Fusion, think of fusing liquid molecules together so they stick into a solid. Q equals M, 0.035, times L, the latent heat of fusion, 3.33 times 10 to the 5. That gives me a value of 1,165 joules. And we'll round at the end. Section 3, well, once we've fully melted our ice, we have 0 degree liquid. We're going to heat it up to the boiling point, so that's Q equals mc delta T. The mass is the same, 0.035, times C, the specific heat of water, 4186, times our delta T. We go from 0 to 100, so that's positive 100. 100 times 4186 times 0.035. Q3 equals 14651 joules. I'm going to do number 4 up here. Well, once our water is at the boiling point, any heat added goes into boiling it. That's Q equals ml. The mass is 0.035. Oops. And since we're going into from liquid to gas, we're going to use the latent heat of vaporization times 2.26 times 10 to the 6. Quit trying to end my slideshow. 0.035 times 2.26 times 10 to the 6. 7,900 joules. Number 5. Once we fully vaporize all of our water, it's at 100 degrees right here. We bring it up to a higher temperature, 108 degrees, so that's Q equals mc delta T, 0.035. The mass is still the same. The specific heat is the specific heat of steam, so that's 2010. And the change in temperature of the steam, it goes from 100 to 108, so that's positive 8 degrees Celsius. Don't understand PowerPoint. 0.035 times 2010 times 8 equals 562.8 joules. Okay, well, we are almost there. We found the heat for each section to find the total heat. We're just going to add up all of the individual heats. So we just add up all of our answers from 1, 2, 3, 4, 5. That's going to be 10, 24 plus 11655 plus 14651 plus 79100 plus 562.8 equals, trying to get me to end that show, I'm getting, I should round it to either 2 or 3 sig figs, but I got 106,993 joules. So I'm going to do 3 sig figs, 1.07 times 10 to the 5 joules. That's the hardest possible heating curve problem you can get, because you had to do 3 temperature changes and 2 phase changes. But the setup is pretty straightforward. Just find the heats for each section on the heating curve. Sketch out your heating curve. And that's that. Those are our problems. Hope that was helpful. Have a great day. Bye.